Hello, universe. I thought I'd make some comments on differentiability. First of all, in n dimensions, if you view a function as a function from n-dimensional space into the real numbers, and you look at its graph, okay, then differentiability can be thought of as the graph being some sort of manifold or surface, and that graph can be locally approximated by a tangent plane. So essentially you can attach a tangent plane to a point. That is the condition for differentiability of a function of from n-dimensional space to the reals. And having a tangent plane can also be thought of as being able to sandwich the surface between two paraboloids at that point. So if you take two paraboloids, two quadratic surfaces, and you can sandwich your surface between those two paraboloids, then you're actually guaranteed you understand the tangent planes of these two paraboloids, and the tangent planes of these two paraboloids agree at this point of tangency here, where the function is differentiable. And so, in fact, this forces the tangent plane of the function itself by the convexity of these two kind of test quadratic surfaces. That forces the tangent plane of the function itself to be squeezed between the tangent plane of this upper quadratic approximation, the tangent plane of this lower quadratic approximation. So in fact, we just need to be able to perfectly sandwich the graph of the function between, or just the function itself, between two paraboloids which are concave and convex respectively. Sorry, this one is convex, this one is concave, right? Yeah. So, anyways, we just need to be able to sandwich the function between these two convex and concave paraboloids, which agree at the point of tangency, and then we're guaranteed that the function is differentiable. And then there's going to be a linear map which takes a plane in the base space here. Let's just draw the base space here. So if I look at the base space here, then if I draw a plane in this base space, maybe this is the coordinates x and y. Obviously this can be n-dimensional. This is the domain. So Rn, this is the domain. Then if I look at this point here, sitting above the domain, then in fact I can attach a tangent plane to this point, and I can look at how this plane in the domain gets mapped to this tangent plane, and that is a linear mapping, okay, called the differential. Let's say the differential at the point P of this function g in question, okay, where g is this white surface that I've graphed here, okay? And so the differential essentially is a mapping of this tangent space into this tangent space, and then another thing you can think of is how mass is locally being stretched or squeezed by the function. Okay, so obviously this is going to be this can be translated into n dimensions to n dimensions. Right now we're just doing n dimensions to or 2 dimensions to 1 dimension. This can be generalized to n-dimensional space, and if it's from n dimensions to n dimensions, you can think of it as mapping a cube into a parallelepiped whose volume is and the volume of the true function is sandwiched between two upper and lower bounds, which essentially agree. So two parallelepipeds, basically. The image of a cube in the domain, is sandwiched between the images of two parallelepipeds in the codomain, and the images of those two parallelepipeds are essentially, they differ by an order of the distance squared. So they differ quadratically, just like in this approximation, okay? And so that means that, in fact, there is a unique linear map which maps the cube into a parallelepiped, an n-dimensional cube into an n-dimensional parallelepiped, who is framed by this. If this cube is framed by my unit vectors, then the frame of the parallelepiped is just the gradient, is just framed by the gradients of all the coordinate functions, okay, of the mapping. Now, in one dimensions, you can view this volume distortion effect if you just look at a function from the interval AB to f of A, f of B, okay? And let's suppose that our function is differentiable, then I'm going to be able to attach this secant line approximation structure, right? So I'm going to basically approximate each of my subintervals. I want to approximate the function at this point by its tangent line, okay? And then that tangent line tells me locally how the function f is stretching or deforming the mass of the real line, okay? So if I picture this interval AB as just having some mass, some uniform mass, this function f is going to be squeezing the interval AB near f of A, and then when we get closer to B here, it's going to be kind of stretching it a little bit more and not squeezing it as much. So like this interval over here near B is actually stretching the interval slightly. And so the derivative measures this local volume distortion, okay? And that is precisely the statement here of the fundamental theorem of calculus, which just says that if I integrate the derivative over A to B, okay, so basically if I attach to each of these intervals, okay, so I sum these intervals, but each of these intervals I scale by the mass distortion of the function. So when I scale by the mass distortion of the function, I'm multiplying by f prime of x. So this f prime of x dx is the scaled length of this small interval dx. I scale it by the f prime, by the slope of this line here. The slope of this line, when I scale it by the slope of this line, it stretches or shrinks the unit interval by the factor of that slope, which is the derivative here. So that's this term here, and it's integrated from A to B. And the second term is just saying, well, that's equal to the total mass of the resulting image, right? Because mass is conserved. So the total mass of the that's basically just the integral of f of 1 from f of A to f of B dx, right? So essentially, this process, this differentiable function, preserves mass. Okay. Well, it distorts mass, but it distorts mass, right, in a way that we can understand. So we can account for the mass distortion here. So basically, yeah, this differential dx in the image can be taken as the differential f prime of x dx in the domain, okay? And then there's an n-dimensional generalization of this formula called the change of variables theorem, and it like generalizes this. And of course, it uses the fundamental theorem of calculus, but it generalizes this to arbitrary dimensions. So basically, it's a generalization of almost a generalization of the fundamental theorem of calculus, because the fundamental theorem of calculus tells us how mass is locally being distorted, right? And this is exactly what this theorem tells us: how mass is locally being distorted. So change of variables is maybe even a little bit of an understatement. This is like a generalization of the fundamental theorem of calculus, actually.